Hello everyone, welcome to the next session on ANSYS CFD tutorials. In this session, we will analyze a 6-digit NACA aerofoil for its fluid flow analysis. We will start by double-clicking on Fluid Flow Fluent. We will first go to Geometry and right-click and import the geometry of 63412 aerofoil. We will double-click on the aerofoil. This aerofoil is of 3D type. I will just delete the extrude part as I want a 2D aerofoil, as you can see here. Now I will go to XY plane and I'll create a new sketch. I'll go to sketching. I'll draw a rectangle over this aerofoil. I'll give it dimensions. This is 200 and this is 100. Also, I'll give the distance between these two lines and these two lines. This is 50 and this is also 50. So now you can see there's a bounding box. Then I'll go to Concept, Surfaces from Sketches. I'll select the sketch 2. I'll choose Add Frozen and Generate. Now I'll go to Create, Body Transformation, Rotate. I'll select the surface body of the aerofoil. Axis is the XY plane and angle I'm going to give it as 15 degree and generate. I'll go to line body and suppress body. I only want to see this aerofoil. Next I'll go to create boolean. I'll choose subtract. Target body is the outer one. Tool body is the aerofoil and generate. So this is the geometry which has been created. We'll close this now. Next we'll go to mesh and double click. So we'll first go to mesh and change the sizing to 0.01 meter and generate. So you can see the meshing is not too fine. So I'll just right click here, insert refinement. I'll select this face, apply and generate. So now you can see it has become much finer. Next I'll rename this side as inlet. Then I'll select this side, right click, create name selection, outlet. This is the top surface. And this is the bottom surface. This is the airfoil. You can select here and see all 5 can be seen. Once this is done, just go to mesh and update once again. You'll get a message here, the mesh translation to Fluent was successful. Once this is done, you can close this window. Now I'll go to setup and double click. So now I'll click on double precision and choose two solver processes and start. The solver type will be pressure based, velocity formulation will be absolute, time is steady, and 2D space is planar. First we'll go to models. I am choosing SST type K omega viscous model. Next I'll go to materials. The fluid is air, so we don't need to change anything. We'll go to boundary conditions, inlet, and double click on inlet velocity. I'll give this value as say 10 meters per second, apply and close. Then I'll go to reference values and double click. I'll compute from inlet. Reference zone is the surface body. Then I'll go to methods and double click. Here you can see the turbulent kinetic energy model is a second order upwind type. Then I'll go to monitors, report files and double click. I'll select new again, force report, drag. Drag coefficient is selected, so I'll write here drag space CD. I'll choose the airfoil, print to console, OK. Again I'll click on new, force report, drag. I'll select drag force and here I'll write drag space force. I'll select the airfoil, print to console, OK. Again I'll click on new, force report lift this time. Lift coefficient is what we are going to select. So here I'll write lift space CL. I'll select the airfoil, print to console, OK. Last new, force report lift. We want to see the lift force, select this. I'll write here lift space force. I'll select the airfoil. I'll select print to console, OK. Once this is done, we'll click on OK and close this. Then we'll go to initialization and double click. We'll choose hybrid initialization and click on initialize. Initialization is done. Then we'll go to calculation activities and double click on auto save every iteration. Here we'll choose say 25. OK. Then I'll go to run calculations and double click. I'll choose number of iterations and say 500 and calculate. Calculation is complete. OK. Let's check where the solution has converged. At the 57th iteration, the solution has converged. Now we want to see the drag and the lift. So here you can see the drag value CD. It is 0.0289. At this point, the value of force is 1.77 Newton. Then we'll go to lift. The highest value is 0.2567 and the value of lift force is 15.7246 Newton. So you can see that the lift value is quite high as compared to the drag and the drag force, which means your airfoil is going to have a good lift value and it will go into the air quite easily and it will experience a good lift. So we will close this now. OK. We'll go to results and double click. We'll first click on streamline. OK. We'll start from symmetry 1. Number of points say 90 and click on apply. So you can see here this is a streamline flow over the aerofoil. The maximum velocity is 34.33 meters per second, which you can see is over here. And over here you can see minimum velocity over the aerofoil. We'll go to animation and we'll see the result. I'll select the type as sweep animation. I'll select the streamline one. I'll make it a bit slower. I'll remove the forever loop and give say 3 loops and run the result. So you can see here this is the streamline flow over the aerofoil. 15-degree angle of attack is what we have chosen, which means it is showing a critical angle of attack, which means your lift is going to be really good, drag will be less, the aerofoil will move very easily into the air. Also, there is no vortex formation. If you want to reduce the size of those balls, you can go to this options. Here, the size of the ball is say 0.5. Okay, and you can play once again. Now you can see the size has reduced. This is just used for indicating the flow over the aerofoil. If you want to save this animation, you can click on save movie and save it in a particular format so that you can use it again. So now we'll close this, then we'll go to contour. Before that, we'll remove the streamline option. We'll click on contour 1, okay. I want to see the contour of pressure, range is local. Number of contour points say I give us 110. Location is symmetry 1. I'll go to render and remove show contour lines and click on apply. So you can see here now the value of pressure is highest here, and here you can see it is lesser than that. The value is 90.26 Pascal, where the color is this reddish color, and wherever you can see the blue color or the yellow color or green color, you can read the values from here. So this is about the pressure. Next we'll create the contour of velocity. So we'll click on contour, okay. I'll select location as symmetry 1. I'll choose variable as velocity. Range is local. Number of points is 110. I'll go to render and remove show contour lines and click on apply. So now you can see this is the velocity contour. Wherever you can see it is blue, it is showing 0 in color. In fact, it is not necessarily 0. It can range from 0 up to this 5.6. As you can see, there's a range over here. So it is not specifically 0 everywhere. And in other places, you can see the value is varying because there's a difference in color. Where the color is red, it is indicating highest velocity, which is 34.332 meters per second. So that's how you can see the flow over this aerofoil in the form of pressure and velocity. Since you can see the coefficient of lift is quite high, you will experience a good lift for the aerofoil and hence it will easily glide into the atmosphere. With this, I end the session. I hope you understood the analysis of a 6-digit NACA aerofoil 63412. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.